So good morning, good afternoon, good evening, and happy, healthy, joyful, friendly, successful 2022. I'm very delighted to welcome you all to the first edition of the Networking Channel program. We're very glad that we have a wonderful session today that is going to take us to satellite communication systems and QUIC. And we have 7 excellent panelists, and I would like straight away to hand over to Nicolas, who I would like to thank for setting up this session and sharing it. Nicolas, the floor is yours. Thanks to everyone, and enjoy the session.
So, hello everyone. So my name is Nicolas, and I was working for the French National Space Agency up to December last year, and I'm now working for a different company. But this is this meeting is about QUIC and some things I did when I was working at the French Space Agency, and with lots of people, and most of them are with the panel, at the panel with me right now. Can you all see my screen?
Yes, excellent,
yeah? Okay.
Nicolas. Everything is fine.
Okay, so I have just 10 minutes sharp to introduce to the meeting. I think not everyone on the meeting today is aware of what is a Satcom system. It's very important to go over some myths that we have, because lots of people may think that Satcom systems are quite specific and very strange. When you look at the figure on the right, you see, okay, this is a 3GPP network. I've seen normalization work. I know how this is working. On the middle, you have an architecture for more fixed broadband systems, which you may be aware of. And for Satcom systems, we have no standard, and so it's very strange maybe to lots of you. Also, sometimes when you speak to Satcom experts, they tell you that it's very strange because basically we have a limited frequency resource. You always have regulation issues. Sometimes in our work, when it rains, you have less bandwidth, so it's something that can be strange. You have to have some to deal with dish alignments and so on. So indeed, the myth in that sense makes sense. But then I guarantee you that what we do is on high level, when you look at the high level architecture, is very the same. Basically, we have a satellite gateway that gathers lots of satellite terminals. We use a DVB S2 standard to communicate with these terminals, and then we have a management network or aggregation network that gathers all the gateways traffic. So it may be so specific, but it's not that different at high level to what you are aware of. We have also been said, another myth is that there is a huge latency in geo-based Satcom systems. So I think that the best way to show you that it's not that bad is to show you what's happened when you actually browsing the web using a satellite access. This is me browsing the web and screening, recording my screen. And as you can see, sometimes when it is congested, this is better to what I have at home. So I think it's very important for us to say that satellites has a huge latency. It has impacts on protocols, and that is what we will discuss today, but it's not that big of a problem for web browsing. Another myth that is not a myth, in fact, is that we have lots of strange middle boxes. So here, the point is not to go into the details of the different functions that happen at the access, physical, and network gateways of the satellite system. The main point is to mention that we have a magic mix of transport technologies. Basically, if you have TCP sessions, we split them and we adapt them to have a good performance over the satellite network. So the slides will be available. So if you have any, if you want to know more of that, there is an excellent RFC 3135 on that. And why do we have performance NSX proxy? It takes a while to set up a connection. Also, we have very high bandwidth and high latency. So to actually fully exploit the available capacity, we may have to do some specific tunings at clients and servers. And also, if you lose a packet on the geo access, basically it takes time to first discover that you have lost a packet, and then to do the correction. And the worst thing is if you have a loss-based congestion control, you may reduce your bandwidth, your throughput by a lot. And also, why we now have geo systems with 50 megabits per second accesses. It makes take a while for the congestion control to actually converge to the available data rate. So for that, if you have an PEP TCP that we use, basically, if you look at the problems I mentioned earlier on, we can improve the connection initialization. We can let connections opened already. We can use lots of magic mix of transport to easily access, to basically easily establish the connections. We can tune the buffers as we want. So that's on the required window size. On the reliability, the loss is spread over the different segments. So if you lose packets between your home router and the computers on the local network, basically you wouldn't have to go over the satellite access again. So that's one of the big gain from the TCP proxies. And also, we can do what we want at the TCP level. So we can have a TCP version that is actually specifically tuned for Satcom systems. So what does PEP TCP does is, the display of the figure is very wrong, but if you look at the bottom, basically it intercepts establishment connections and take the place of the endpoints. And so we have 3 different connection establishments, and that can, so yeah, you have 3 different connection establishments, and then you have a specific congestion control on the satellite system. And with that, basically, when it can take, if you look at the bottom left figure, if it can take up to 9 seconds to download a web page without proxies, it can be reduced to 4 seconds with proxies. So the problem is, or a good thing is, that will be the main topic of today's meeting, is that QUIC protocol has been deployed for lots of Google services since 2012. It has been really recently standardized by the IETF through a different RFC series, which numbers on the slides, and it is more or less 30% of the broadband traffic. If you look at how the functions are spread over application, transport, and network layers of the system, you can see that QUIC basically does a mix of TLS and TCP. So it takes the confidentiality and the flow and congestion controls and reliability, and everything is on top of UDP. So the big thing is basically we can't use our problems, and so we have QUIC end-to-end, and the main thing is what is happening on these different points. And so this will be the main topic of today's discussion. And to assess that, basically, next on the floor will be John and CJ from Hughes to speak a little bit about QUIC and Satcom PEP and traffic classification. And then Christian Huitema will speak about how we can tune QUIC to avoid using PEPs. We will have some operation constraints from people from Orange, so Isabelle and Alex and Emile, and then Marie-José, sorry for the issue on the affiliation, Marie-José from Telecom Paris, that will speak a little bit about low Earth orbit and all these SpaceX satellites that we have been hearing all about. So, and there will be lots of room for discussion as well. So please now I let John share the screen if it works, and if I can share them if you want. But
I'll do it myself.
If you have, okay, okay. So thank you very much to all the panelists that agreed to participate and share their views on this very interesting topic. So I let you the floor, John.
Okay. Let me change the view here. Anyway, I'm going to talk about PEP and traffic classification. I've been working for Hughes and with geosatellites for 35 plus years. So I have a lot of experience with this. So basically, at a high level, I left off an important one that my coworker brought up, which is what we're trying to do with the PEP is you're optimizing over the satellite, that protocol, and then you're locally handling the TCP on each end to allow local congestion control and in particular local recovery packet swap. Another one that I did leave off here is it also greatly reduces the ACK traffic that has to go over the satellite, and that's particularly important in the uplink direction. So Nicolas touched on these, but basically, if you lose a packet on the Wi-Fi link at the terminal site without a PEP, you're going to have to recover that all the way across the network with the high latency, and it slows everything down. And if you lose one on the satellite link, well, we can apply even link layer recovery there, but for the end-to-end stuff, it's the PEP lets you do it locally on each side, and that's one of the most powerful features. And it's become even more important as the networks became wireless at the terminal sites. And then over, as I mentioned, over the satellite link, we optimize because we're using our proprietary solution over the satellite to recover from errors. Well, I spent a little bit of time talking about that. Something that doesn't get talked about a lot is traffic classification. There's the Wikipedia definition. I won't read that to you, but basically classification is primarily based on transport header information. In particular, TCP and UDP port numbers are the most basic classifiers. So for network operators, traffic classification is important to meet the SLAs. You work the traffic classification and the PEP work hand in hand. In our own particular system, we have up to 8 different PEP backbones to support the traffic classification. Different classes go with different PEP tuning. The last mile is really the first mile when it comes to traffic classification. You need to be able to decide what, you see the end user initiates the traffic, and you're trying to decide, is this interactive, is this background, is it streaming, and assign the resources of the network based on that. And there may even be multiple paths with different characteristics. We at Hughes have hybrid satellite and terrestrial solutions. And so all the traffic classification is all involved in that. So with QUIC, encryption is mandatory for good reasons. QUIC encrypts not just the payload, but also the transport header information. So that hides that information that the classifier is primarily using to decide how to do it. So without being able to see those headers, you have to do the slow start and congestion control end to end. Although, there's potential things you can do there, which Christian's going to talk about. Error recovery, what's happened end to end, that's one of the ones that concerns us a lot. And all the traffic kind of looks the same, making classification difficult. You have to use deep packet inspection type techniques, which at this point, it's not clear how well those work on QUIC, but I'm sure it will get better over time. So that, that's the impact that the QUIC has on it. And that's my last slide. I'll hand it over to Christian.
Thank you, John. Okay.
Thank you, John, for presenting the case and the reason why we have this performance enhancing proxy. I'm Christian Huitema. Oh shit, I'm sharing the wrong slide. Damn it. Where am I?
So you are sharing, making QUIC work with satellites.
I am sharing that.
Yes, that is what we see.
Good.
January 19th.
Good. I mean, I was very concerned because I had a couple of different programs. So let's go directly to what we see. I have tried to summarize the debate on a simple slide here. And the simple slide shows the real two views on the problem. And the two views are that what John just presented, that basically without PEP, TCP would not work with satellites, and we have an RFC for that, etc. And you have the QUIC view, which says that performance proxies, in fact, every proxy whatsoever is an horrific kludge. It causes ossification. It let the network operators mess up with the way we send packets. So we are going to use encryption to destroy all these proxies, make sure they don't happen. If they ever happen, I mean, if someone managed to do traffic classification without encryption, we'll treat that as a bug and we'll fix it to make damn sure they don't work at all. So that's pretty much the philosophy of QUIC. So the fact that performance enhancing proxy do not work with QUIC is not a bug, it's a feature of QUIC, it's by design, it's exactly what QUIC wants to do. Mission accomplished, great. Now, of course, if we do that, we have a small problem. John alluded to that, and Nicolas mentioned it too. Basically, the problem with TCP can be resumed as issue with TCP slow start specifically. The fact that when TCP starts, it does that with ramping up the congestion windows progressively in the beginning of the connection, and basically doubling it every round trip. And doubling it every round trip is okay when the round trips are short, but when the round trips are long and when your projection window is big, it takes quite a time. It can, that's the main reason. If you don't do anything in particular on a 100 megabit per second link with TCP, it will take a good 10 seconds maybe to arrive to the full bandwidth capacity. So that's a problem, clearly. The same problem that actually happens inside the connection if for some reason we have TCP detecting a high congestion, it shuts down everything, goes back to the beginning and restarts. And again, you will take another 10 seconds to ramp up. Next issue is loss recovery. Loss recovery, the main impact is with the latency, that effectively it takes a full round trip to correct the loss. So that's an issue. If you have too many losses, you will see an impact on the congestion control, TCP congestion control, where very sensitive to losses because they use loss as an indication of congestion. So if you have too many losses, then you get to slow down the connection, and that takes a long time to ramp up. And then if you have too many losses, you may saturate your your loss recovery system, because loss recovery is efficient because you can flag individual losses pretty much. But if you have too many of them, that makes the packets, the ACK packets, way too long. And so you cannot correct those losses individually anymore, and everything slows down. Point that John mentioned as well, ACK congestion. Take the common case of satellite channel. It's very often that we have an uplink that is limited in bandwidth. And so if you do that, then your classic TCP control will send acknowledgement every 2 packets. That will create way too much traffic, and that will bog down the congestion. So I have been working with Nicolas and the Intosat working group in QUIC a couple of years now, and we have been looking at how to solve that. And the good news is that we can. First, the connection startup. The main way to solve the connection startup issue is to remember previous connections. So if we remember previous connection and we have that in memory somehow, something that we are trying to standardize with the EBDP option in QUIC, then when the connection starts, it says, oh, okay, this is one of those high bandwidth, long delay connection. I know what I shall do, and I can start immediately. Now, if you do that, you'll start up not exactly immediately because you want to do some verification to make sure that conditions have not changed and things like that. But you will start up in, say, 1 second or 2 seconds instead of 8 or 10. So if you are restarting an existing connection, problem solved. If you are not, you can still do things, and I implemented that in the QUIC implementation of QUIC I've been managing. And basically, the trick is to do bandwidth evaluation during the source start step. So instead of spacing all the packets one by one to make sure that everything is sent smoothly, you deliberately create disorder by sending packet trains. And by timing those packet trains, you can get an estimate of the bandwidth of the link. And if you observe after a couple of round trips that the link is actually high bandwidth and the delay is long, then you can ramp up your congestion window much faster than TCP predicts. And that way you can into a working state sooner. To think we observed in practice is getting in the working state in about 5 seconds instead of 10 with this trick. For loss recovery, the first thing we did was to change the congestion control algorithm to use congestion control algorithms that are not so sensitive to packet losses. And the good news there is that new congestion control algorithms like BBR do not react on losses. Well, they do if you have catastrophic losses. If you have losing one packet from time to time, the transmission remains at a high rate and doesn't slow down. So that solves a large part of the problem with packet losses, which is not so much the fact that you have to correct the losses, but the fact that you have to ramp up congestion. The QUIC ARC frames are much larger than the TCP ARC, so you can carry a number of ARC branches. So we have done a test of having losses of a few % packet on a high bandwidth link, and it goes just fine. We have not done the test of developing forward error correction for QUIC. I have done some small things. Other teams have done those tests, but that's something that could be done in QUIC as well if it was needed. As for ARC congestion, we've been lucky that ARC congestion is also a problem on every high bandwidth link. And it's kind of not due to the uplink in the case of high bandwidth terrestrial connection. It's due to the fact that frequent ARC will interrupt the sending process and cause a CPU overload. And because too frequent ARC cause CPU overload, then, and also break things like transmission offsets, then everybody in QUIC is trying to reduce the frequency of ARCs. and developing things like the delayed arc extension, which is an addition to QUIC that's very well adopted, and typically result in sending an arc for 64 kilobytes of packets. So basically, the high bandwidth system sends a bunch of packets, typically 64 kilobytes, just in a single shot. And then the receiver received all of them in quick succession and sends the arc at the end of that. And that do not say that the window is 64 kilobytes. The window can be megabytes, but sending that by big chunks helps a lot in the arc conditions. So basically, my point is that all these enhancements of QUIC for satellite have been implemented and they have been demonstrated in the PicoQuick implementation of QUIC, except for FEC. And I am pretty confident that if you use a PicoQuick for your QUIC implementation, the end-to-end solution will work just fine. Now you may say, okay, satellite experts have heard that before, but the problem is that there are many implementations of transport protocols. And so maybe the PicoQuick implementation is great, but if if the customer is using a different implementation that is not optimized, what do we do? Well, it's tough because I repeat, you cannot use the performance. The design, QUIC work very hard to make sure you don't. So the question is basically more implementation shall implement those options for satellites. And my mantra there is that you have to test them. If it is not tested, it probably does not work. That's true of pretty much every computer system, but it's very true of trying to do satellite communication with QUIC. So that's actually how we did that in PicoQuick. We didn't start from the solution. We started from the test. We added in the test suite a bunch of simulation of satellite links with various conditions. And we looked at what was happening and we verified that all the tests passed in the end. So then those scenarios, those kind of tests, implementations may or may not do them. I mean, most implementations do test for the scenarios that they do support. A typical implementation by the big guys like Microsoft or Google will have hundreds and hundreds of tests that they do that represent the main case of their customers. And so if satellite communication is a main case, they will do those tests and it will work. If satellite communication, and specifically if geostationary satellite communication is not mainline, then it becomes excellent. And then you are kind of in a harder place because exotic scenarios require specific solutions. The good news is that something are mainline. As I said, I mean, the delayed arc extension is mainline. BBR is mainline. EBMP, the extension that makes people reuse previous condition on the link. I mean, scenarios like that have been used on a variety of channels. They're also generically useful for high bandwidth connection. So they will be mainline. The other good news is that a lot of things, if you can do the delayed arc extension, if you have EBMP, then there are a lot of things that you can do in a server. So then that will work with clients. I mean, the clients don't have to mess up with the window. They don't have to mess up the congestion control. They just have to send the acknowledgement not too fast. And if they do that, server-side implementation will be sufficient. So if you are surfacing data from a high bandwidth satellite, picking your server implementation will work. So I'm trying to not be too long and stay in time. But my conclusion is, I'm pretty sure that QUIC will work with satellite. if we want to make it work. And no, we don't need the performance enhancing proxy anymore. That was something of the 90s. Thank you.
Thank you, Christian. Indeed, okay.
Hello, everybody. You see my presentation?
Yes, perfect.
Yes, so good.
Okay. So I'm Isabelle Hamchaoui, and it's a pleasure to have been invited to this panel. And with my colleagues from Orange, we will be giving you a quick look on operational issues raised by QUIC in Orange networks and more generally in very large networks, including satellite or not. Indeed, QUIC has major impacts on our monitoring and troubleshooting process, which are very important to maintain our network's health and consequently provide a good experience to our customers. So let's get starting. So first of all, what is QUIC? I think that you're all very familiar with QUIC, especially after the previous excellent talks. But I would like to remind you some facts about this protocol, which have some consequences regarding operational issues. From a political point of view, QUIC is born just after the NSA eavesdropping scandal. And this has caused a general suspicion towards state agencies and also ISPs, who were generally considered as their accomplices. As a consequence, QUIC was designed so as to preserve user privacy, not only on transmitted data, but also on linkability. That is the ability to track user activity across the internet. And this feature has a strong impact on many operational processes. Moreover, QUIC counts for about 30% of Orange network traffic, and it is still growing. It's now an IETF standard. It is part of the standard HTTP free stack. So it's definitively not a small issue. So we should really consider it in any of our operational process. From a functional point of view, QUIC is a transport protocol very similar to advanced TCP versions. For practical reasons, QUIC is encapsulated in UDP packets, but it should be seen as another TCP version. And as you already know, TCP is responsible for connectivity between endpoints. It means that it ensures integrity of transmitted data thanks to a control loop made of data packets emitted by the source and acknowledgements sent in return by the destination. And QUIC does exactly the same, but with header encryption. And in this case, headers are no more readable from intermediate nodes. So what does it mean? What does it mean regarding network operation? In fact, it means a lot, especially for network troubleshooting. That is the detection, location, and fixing of default nodes or segments in our networks. ISPs used to detect and locate faulty equipment by monitoring loss and delay on customer traffic via one-point measurement. In the TCP world, which is represented in blue on my slide, the easiest way to do it is simply to observe the TCP connection anywhere on their path. On my drawing, on the top left of the slide, you can see a TCP connection in blue with its famous control loop made of data packets and acknowledgements. The packets are numbered sequentially by the source, thus a missing packet in the series is very easy to detect. And thanks to TCP packet number and acknowledgements, you can also monitor the delay between a packet and its acknowledgement. And you can detect delay degradation. For example, an increase that generally denotes congestion. Missing packets and increased delays indicate a default. But what is much more important, in fact, it gives information on where this default is located. For example, on my left-hand side blue drawing, missing, if the probe sees a missing packet in the series, it also deduces that the lossless segment is upstream from it, from this measurement point. That is, it is between the server and the probe, even if this segment is outside the operator domain. And similarly, downstream loss can be identified with acknowledgements. When loss is detected, for example, you just have to move the capture point, thus cutting in half the suspicious segment again and again, till locating a node or even a card by dichotomy. And on the right-hand side of my blue drawing, you can see an example with a dichotomy in 3 steps, which leads to the isolation of a faulty segment, which is in dark blue, and which is very small, and probably is just a card. And then you just have to go and fix it. So it's wonderful. It's a very powerful tool. But what happens with QUIC? With QUIC, there's no more readable packet number. So, and it's even impossible to know whether a packet, it's a data packet or an acknowledgement. So this process cannot be reused. So what can we do in this very challenging context? In fact, solutions have been proposed to restore loss and delay observability. And the first one for RTT, for delay, is called the spin bit mechanism. It's a compact and very elegant solution proposed by Christian Huitema. Thank you, Christian. And it relies on 1 bit in clear in QUIC packet header, which toggles every round trip. A probe observing packets on the path can then deduce the round trip time as the time between 2 toggling. This mechanism is called a spin bit, and it has been accepted in QUIC v1 standard as an option. The second mechanism relies on the so-called loss bits, and of course, it is a mechanism for loss measurement. It requires 2 bits in clear in the QUIC header. With one of these 2 bits, the source draws a reference pattern in the packet flow. That is a block of n packets with the same marking, then a block of n packets with the opposite marking, and so on. And this mechanism thus delineates slots of n packets with the same marking. Observation points can estimate the upstream losses by simply counting the packets in each slot, and thus they can locate by dichotomy the faulty segment, just as for TCP. And the second bit is dedicated to downstream loss. So wonderful. But what are the takeaway messages regarding operational issues with QUIC? I think that there are two main messages. The first one is a risk because of the loss of K indication for ISPs. It is really a strong risk because without any observability, ISP will not be able to proactively detect QoS degradation, and they should wait for a customer to call the hotline to react. So it's not very comfortable for ISPs nor for customers. And it probably may lead to QoS degradation. Moreover, in this case, there's no easy way to distinguish between different actors' responsibility, and it may become very quickly a very tricky problem. So the second message is that there is some hope, because there are some solutions for quick observability. The first one being the spin bit, which is in the V1 standard, but unhappily, it's shipped in QUIC V1, but it's not activated by the big players because they are very suspicious toward anything which can say something about the traffic. And moreover, regarding the loss bit, it's worse because there's no IETF consensus, and there's only interest expressed by CDN provider, especially Akamai, and few operators, including, of course, Satcom and Telecom Italia also, by chance. But nothing changed now, and we hope that it will change soon. So if you want to go deeper in the subject, we've got some references at IETF. And I thank you for your attention, and I give back the floor to Nicolas. Just in time.
Isabelle search, it seems Nicolas either has a mic problem or has been disconnected. So maybe we can just hand over to next.
I think it's me, right?
Yeah, Marie-José, why
Marie-José, yeah, hold on. I'm going to share my screen.
Yeah, Isabelle has to withdraw a screen from
Excuse
Zoom.
me. Excuse me. Is it okay now?
We still see your screen, Isabelle. Yeah, no, it's good. Now we have Marie-José.
Okay, so I'm Marie-José Montpetit. I'm an invited scientist at Telecom Paris Sud, and actually, Serge, I saw with happiness that you are part of the PAWR project, because I'm actually also collaborating with Ohio State University, that is also part of this this consortium. So I was asked by Nicolas to do and now for something completely different, which is how I used to introduce my presentation when I was part of the architecture team at Teledesic. It is the brand new world, or the brand new old world of low Earth orbit satellites. And so there's the new LEOs and the old. The background is Teledesic. We were from probably 1995 to 2000, the enfant terrible of the satellite world, 750, then 288 satellites. We had optical inter-satellite links for mesh connectivity, and we did a lot of fun stuff on routing, and people thought we were crazy, and probably we were, and suddenly it led nothing. We did a few launches, and we actually, I think, proved that you could apply manufacturing to satellite production, but it went kind of down for a while because there was no, I would say, killer app for it. And suddenly there are killer apps. The killer app is obviously self-driving cars, amongst others, that need connectivity to the internet all the time. And obviously it is not possible everywhere on the planet. So there's now a ton of new systems that are announced. Starlink, which is the SpaceX from Elon Musk, in excess of 4,000 satellites Kuiper from Amazon, which is in excess of 3,000. So, you know, our 750 now looks like so puny, it's incredible. OneWeb Airbus, also in the thousands of satellite. Somebody mentioned before Lightspeed, which is Telesat Canada, also in the hundreds, if not the thousands. Viasat also is thinking about it. Samsung is thinking about it. So suddenly there is a tremendous amount of interest in low Earth orbit communication, to the point that Aaron Falk, who used to do TCP-SAT with me and us years ago, is now moving to define a way to look at satellite debris. So there's going to be a lot of these things. There's been a draft by Lynn Han and Richard Lee of FutureWay, who are not on the call, sadly, that looked at the problems and requirements in satellite constellation. I would say it's a nice read. It's very routing orientated, so it's not QUIC at all. It's not access, it's very routing, but it has actually summarizes some of the features of all these systems, and it essentially has a lot of information on the planes and everything. I'm not going to talk about all of these. I'm going to talk about the one that everybody talks about, which is Starlink. So Starlink is an extremely dense constellation. It is not polar orbit, it is inclined, 53 degrees, which means that there are areas really in the north, especially here in Canada, that will not be covered. I have to tell you that at first Teledesic was polar and we're going to have things everywhere, but there were some issues there, especially when the satellites were crossing at the poles. So at the end also we had gone to an inclined orbit. There's been about 1,800 that have been launched already. The Falcon X has had the most launches in the year. They launched them 44 at a time, so they're stacked. Actually, we also had that ID in Teledesic. SpaceX, which is the company above all of this, has permission to operate about 4,400 satellite. I think that's their latest filing at the FCC. At about 550 kilometers. This is the reason that they need so many satellites to do the full coverage. Teledesic at 750 were about 1,000 kilometers. When we went to 288, we raised 1,200. There's no ISLs in Starlink, at least in the first generation. They've added ISLs actually they had a launch, I think, last week to avoid needing the gateways in the Arctic. Their model, I'm going to talk about it, is not about routing from satellite to satellite. It's actually reaching the next gateway. And so since there are no gateways in the Arctic, they need to do something there. At first they wanted to do KU, then they went KUKA, and that's actually has issues in terms of availability, because everybody knows that in KA and the type of weather that we're having today in Montreal would not be very good. Again, 24 orbital planes, 53 degree inclined orbits. They already have service in some areas. I know people who have it. They want to have speeds up to 1 gigabit per second. The latency is obviously way lower than for geostationary orbits, between 25 and 35 millisecond. I'm going to come back to this in the context of QUIC. And they currently say that they have 140,000 users who pay $99 US per month plus $499 for the access point. And maybe nobody on this call is interested by antennas, but it seems that the antenna is the problem because they need to track a satellite that flies over really fast. They also claim that they've had in excess of 15 million people who have inquired about the service. So connectivity aspects. So how do they do this? It's essentially an access network. There's an uplink and tablish with the satellite that flies overhead and forwards the traffic to a gateway inside its footprint and onward to the internet. They, however, use satellite diversity to maintain the best connectivity in Ka band. So if you have some problems with a rain or fog or something that cuts your Ka band, you can actually change satellites. It may be changing the gateway because maybe the new satellite that you'll find may not be, and it's all may because it all depends, it's statistically. And that's where, for those of you looking at networking, all things that you may be, may not be, may happen, it's always an issue. Again, there's no ISLs to maintain the same gateway, and the ISLs actually may only be turned on at the Arctic because, again, I think this is something that may be missing from the draft, or actually the version of the draft that I looked at. Actually, we know at every moment where every satellite is. And so when you know that that satellite is over the pole, you can turn the ISLs if you want to. And the ISLs that we had in Teledesic were allowing us that once we would establish an end-to-end connectivity, we would actually go to that destination. We knew how to route over the satellite to go to that destination. Without ISLs, you are dependent on the gateway that is in your footprint. The LEOs, or somebody called them the VLEOs, the very low Earth orbit, because those things are kind of twice above, just above the, 250 kilometers above the space station. They don't have large delays, but they have delay variations. And even with ISLs, the routing through the constellation incurs variations. The 35 to 35 millisecond is actually the time it takes to get to the satellite and back. But if you need to change satellites, if you need to change gateways, the actual delay may be different. And one thing is that delays also happen in the ground internet, so it may not be a big issue, but in those things, it is not the delay that's the problem, it's the delay variation. And actually, we were experiencing that in Teledesic. The connection to the same satellite, depending on the actual orbit that they're going to have, you keep the connectivity to the same satellite from 100 to 400 seconds. In Teledesic, we were calling that the 7 minutes. And you will do a make before break before the handover. So you actually connect to the next satellite before you connect to the one that is going over the horizon. Again, this is issues for things that are end-to-end and end-to-end protected. And that's why we're having this conversation. So the impact on QUIC is actually, there's not been a lot of experiments. And thank you, Christian, when you said that, yes, testing, it will work, but it's testing. I do not have the impression that the service that is being offered right now is blocking QUIC, but we don't know. Starlink, for example, is not particularly transparent. It's really hard to talk to the people who actually are working on it. I have to say that I know a little bit more about Kuiper, the Amazon system, because I have a friend who works on it, but obviously she's not allowed to mention too much of it, but there's not been experiments. The idea is it must be working. Some performance aspects, actually. It's the idea of these multiple and changing gateways. It may have a lot of impact, and I think it will have a lot of impact on congestion control. If you change gateways, is that gateway as open as the one that you had established connection to in the first place? There's end-to-end connectivity aspects. It's highlighted in the routing draft, this idea that your path will change. You may get, again, you're going to, even if you have a ISLs, your path will change. But the ISLs would help keep the endpoints constant, and then the magic would happen inside the constellation instead of needing to happen at the endpoints. I mentioned the impacts of delay variations. It may or may not be an issue. I don't think there's been a lot of work on this. What I've seen of people who have tried Starlink here in Canada, actually in some remote areas, is that the K-band issues are a big problem. So there are huge fades, and so the service ends. Is there, well, and the idea of using FEC or not at the network layer to at least protect again some of the errors that could happen while you're still under the same satellite. And I don't think that's been very mentioned, and QUIC FEC, which I've been part of, has not been implemented. The question is LEO connectivity different or similar to mobility in general? In that case, it's the user that's fixed. And it's the satellite that moves, and it moves really fast. And it's not the same as aeronautics, because aeronautics, they keep connectivity with the same satellite, even if the plane moves really fast. There's lessons from 5G. It's discussed in the hand draft. But again, this is the brand new, the whole new world, and we don't really, there hasn't been a lot of experiments. And since there's only 1,800 satellites out of the 4,000 that are being, that have been launched, there's not like a lot of viewpoints still on what would be the whole connectivity aspects and how the performance works. So some questions that actually Nicolas and I discussed, maybe there are already some features in QUIC that could help multipath. You could maybe establish connectivity over multipath to the potential gateways where you're going. You could obviously use connection migration when you move from one gateway to another. And another question is, if they're right that there's over 140 million people who ask about the service, or 14 million, but anyway, a huge amount of people, would there be enough users to justify specific LEO related changes to QUIC beyond what Isabelle mentioned, using maybe the spin bit or other things to see how the performance works, and besides what's already in multipath and connection migration? And those are questions I don't have answers. Again, for me, it's a little bit back to the future, thinking about all these ideas about how LEO work. So the next step, there's obviously stuff at the IRTF and IETF and outside. There's actually plans for a broad scope satellite tutorial at the IETF that would include QUIC. It's because there's a lot of people who have sent drafts. Again, because they look at routing, I think because they're routing people. And so routing for them is very important, but I think there's transport aspects also. So maybe we would like to have a QUIC specific draft. Could there be a QUIC over satellite transport subgroup in the same breath as John is going to say again, Back to the Future? Same breath as TCP SAT of old, who had looked at the aspects of TCP over satellite. And I was at Teledesic then, and we had decided to participate because while we didn't have some of the issues with PEPs or with big, large windows and stuff, we did have issues in TCP, again, due to congestion control and the effect of satellite delay variation. Non-IETF, IRTF, or you guys involved in operations, that could be really, really nice to run experiments with the existing satellites and do telemetry on these existing satellites and these experiments. And maybe we want to start specific ETOSAT discussions and activities. And that's it for me. I thought the end was near for LEOs, but actually I think it is just the beginning. Thank you.
Thank you very much, Marie-José. Can you hear me?
Yes,
Yes.
I hear you very well.
Yes. Okay. So I think we have not very time for questions. I think thank you very much to all the presenters. Sorry for not having time for more discussion open for the panelists, but we have the Slack open for those who want to discuss further on the issue. And I hand over to Serge for the presentation on the next meeting. Thank you very much to everyone. Serge, we cannot hear you. We can see your screen, but we cannot hear you.
I am sorry, I was muted as well. So I was just saying gratitude to all the speakers. Thanks a lot for this very informative and exciting topic. The program has been recorded, as you know, so it's available on our YouTube channel. Likewise, you can continue the discussion if you have questions on the Slack channel, which has been disseminated today through the different means. As you might know, the networking channel not only address very deep technical questions as we had today, but also questions related to education in networking, as well as more broader societal questions. And we are very pleased to announce that the next program, so in 2 weeks from now, because it's always every second Wednesday at the same time, is going to talk about how we can improve diversity and inclusion in the systems and networking community. So please disseminate, please join us in 2 weeks from now. And if ever you have interesting topics that you would like us to share and broadcast in the networking channel, you can always contact us. Thanks to everyone. It was a pleasure. And stay safe and enjoy. Bye-bye.
Thank you.
Bye.
Bye-bye.
Thank you. Bye-bye.
Bye.
Bye.